Welcome to the Materials Science lecture on plastic deformation of metals. In this session, we will explore the fascinating world of how metals change shape under stress. By the end of this class, you will be able to describe various geometries involved in metal processing, explain the concept of plastic deformation, and sketch how dislocations move within metals. Plastic deformation is an irreversible process that increases internal energy. Different methods like forging, rolling, drawing, and extrusion reduce the cross-sectional area of metals, transforming them into desired shapes. Let's determine the forming methods for different components. Match each item with its corresponding forming process: forging, rolling, drawing, or extrusion. Now, let's review the answers. Each component has a specific forming method that best suits its shape and function. The model of plastic deformation by dislocation motion involves slip, where dislocations move through the crystal lattice, causing deformation. Watch this animation to see how dislocations move within the crystal lattice, illustrating the slip motion that leads to plastic deformation. Strengthening metals involves impeding dislocation motion through interactions with defects like solutes, other dislocations, and grain boundaries. Cold working increases dislocation density, which enhances yield strength and tensile strength. However, annealing can lower dislocation density, affecting the metal's properties. Dislocation interactions can either increase strength through repulsion or increase ductility through attraction and annihilation, balancing the metal's properties. As cold work increases, yield strength, tensile strength, and ductility change. Understanding these effects helps in optimizing metal processing techniques. Adding a weaker metal like nickel to copper increases the strength of the alloy. This process, known as solid solution alloying, enhances tensile strength and ductility. Impurity atoms distort the lattice and generate lattice strains, acting as barriers to dislocation motion. This solid solution hardening mechanism strengthens the metal. Grain boundaries act as barriers to dislocation motion. Smaller grains provide more barriers, shortening the distance dislocations travel before encountering a barrier. The Hall-Petch equation relates yield strength to grain size. Smaller grains result in higher yield strength, demonstrating the importance of grain size in metal strengthening. Let's apply our knowledge. Determine the yield strength, tensile strength, and ductility of a cold-worked copper rod. Use the provided data to find the correct answers. Review the answers to the inquiry questions. Understanding these values is crucial for predicting the behavior of metals under different processing conditions. To recap, you should now be able to describe geometries in metal processing, explain plastic deformation, and sketch dislocation motion. These concepts are fundamental in materials science. Thank you for watching. Please like, share, and subscribe to this channel. Leave a comment below about what you learned and what topics you'd like to explore further. This presentation contains copyrighted material used under the Fair Use Doctrine for educational purposes. All rights belong to their respective copyright holders. Links to relevant resources are provided in the video description.